All right, so we're going to take a look at another complex circuit, and we're going to apply our Ohm's law table onto solving this. Now this one I've made a little bit more complex. We have a 9-volt battery here, and then we have a junction here that splits off to a host of resistors over here, and then another path that goes off through another resistor here. They meet back up over here and go back into the battery. Now, to make this even more interesting, I've also got a minefield of information that I've withheld. So for instance, let's say the following. I go through and I know that I put a 9-volt battery in. I set this to voltmeter, put it across like this, and I can measure that it would be 9 volts. And then I go through and I check this resistor B. I know that it's a 60 ohm resistor, and I measure that it has a potential difference of 6 volts across it. I know resistor C is 10 ohms. I do not know resistor D or A. Finally, resistor E is 10 ohms. And the last thing that I know that I give in this problem is I set this over to an ammeter instead, and then I check in here and I see that the current going over this way from this junction is 0.2 amp. So on this one, I've given you just kind of a hodgepodge of different pieces of information. We don't know all of the resistances, so we can't do equivalent resistance like we've done in some of the other ones. So one of the best things to do when you've got a system like this, where you've got kind of a hodgepodge of different information, is to use the table, and let's start filling in the table. So I know my total potential for the circuit, that's my battery, is 9 volts. I'll put that down. We also know that the potential difference across B is 6 volts. So I'm going to put that in. Those are the only potential differences that I know, so moving onward. Let's fill in some of the resistances. I don't know A, I don't know the total resistance of the circuit, but I do know B, it's 60 ohm. And I do know C, that's 10 ohm. And I do know E, which is also 10 ohm. Now the last piece of information that I have, and this one's easy to overlook, but I've got it drawn in here, is that the current going off this way to the right from this branch is, let's see, 0.2 amp. Where do I put that? Well, here's where you need to remember how current works. Remember that the charge is flowing through the circuit. And so if I have 0.2 amps going this way, then I also have to have that going through C and through D and coming back in over here, because the current through this section needs to stay the same. Charges are not used up in the resistors. So I know from this that the current in C is 0.2 amp and that the current in D is also 0.2 amp because it goes through both of those and joins back up over there. Great. So that's all the information that I started off with. We can see that there's a lot of missing holes in my table, and we've got 5 resistors that we're looking at. All right. On the upside, the point of the table is so that you can easily and reliably apply Ohm's law anywhere in your circuit. We cannot simply take the 9 volts and apply it across resistor A, nor could we do that simply for B, or I should say more accurately that it's not a safe bet to do that. That's what the table allows you to do. It lets you know where you can apply Ohm's law and where you cannot. Ohm's law applies on any of the individual resistors, so the potential difference across A will be equal to the current going through A times the resistance of A. Now, unfortunately, we don't know any of those things for resistor A, but we do have for B, we've got 2 pieces of information. So I have 6 volts equals the current through B times 60 ohms. So I'm going to do 6 divided by 60, and I find that the current going through B must be 0.1 amp according to Ohm's law. Great. Well, that gives me some useful information here. Well, before I get too offset on that, let's go through. Hey, there's another place where we can solve Ohm's law. We've got resistor C. Now, don't feel that there's a specific order that you have to go in on these things. Again, until you get a lot of practice on this, many times it can be very difficult to predict what you need to do to get your answer. That's the other nice thing about the table. As long as you're filling things in on it, you're making progress. So I would have 0.2 amps times 10 ohms, and that would give me 2 volts. We've got 2 volts across resistor C. Great. I don't have any other spots where I can apply Ohm's law because I've got too many holes in my table. So it looks like we're going to have to do some more work on this. Okay, let's see. So I have successfully filled in 2 of my resistors, but I need some more information. I don't have anywhere else that I can apply Ohm's law. I might be able to do something with equivalent resistance, but for the most part, I don't know the small section of my circuit, and there's a bunch of stuff that I don't know about my circuit overall, so I probably can't do anything moving vertically in resistance column. Well, I could use Kirchhoff's junction rule to do something in the current column, or I could use Kirchhoff's loop rule to do something vertically in the potential differences. Let's go ahead and look at junction rule, because we haven't applied that as much in the videos we've looked at thus far. And we just finished filling in some currents. So, here we go. I've learned something important, that I know that going through C is 0.2 amp, and since there's 0.1 amp going this way, going through B, that means that since I have 0.1 going this way, 0.2 going this way, what must be coming in by Kirchhoff's junction rule is 0.3 amp. And where is that coming from? It's coming from resistor A, which means the current through resistor A must be 0.3 amps, because that's what goes through here, comes into this junction, 0.1 goes that way, and 0.2 goes the other way. Now, be careful with this, because in many of the other ones, we had it that what was going through A was the total current of the circuit. But it's not, because we have a current coming out of the battery here. Some of it goes off towards A, but some of it goes off towards E. So all we can tell is that 0.3 amps is what is going through resistor A. It is also what is coming out over here, because they come back together right there. All right, well, we've filled in a little bit, so that's some useful information, but we've kind of got stuck now with what we can do with junction rule. Okay, that's fine. So once again, we don't have enough information to do anything useful, I'd say, with equivalent resistance, at least not without getting really clever. Our currents, we've filled in as much as we can. So let's take a look at loop rule. And for loop rule, let me grab some additional markers here. Let's go with a loop. Now remember Kirchhoff's loop rule. I'm certain you're tired of hearing me say it, but loop. You must apply this over a closed loop. So I'm going to start on the far side of the battery, which is what I like to do. We go across the battery, and the battery gives us plus 9 volts. Now I'm going to keep going. I'm going to come this way, because that's the main part of the circuit that I actually know a lot about. And I go across A, but I don't know the potential drop across A. That's okay. Maybe that's what I'm looking for. Delta VA. Great. And then I keep going. I come down to this junction here. And I'm going to go to the left because there's only one resistor over there, and I've got all the information about that resistor. I go across B, and it brings us down by another 6 volts. Remember, resistors lower our potential. Batteries will raise our potential, at least the way that we're working with them. And then we come back over here, keep making our way over to the far side of the battery, and there we go. We have a closed loop, which means that these must add to 0, which gives us the following conclusion, that delta VA must be 3 volts. Great. This is applying loop rule. 3 volts. Great. Okay. Well, now we've filled that in. Now we can quickly find the resistance of A. So why not do that? We would have 3 volts divided by 0.3 amp, and we end up with, hey, resistor A is another 10 ohm resistor. Great. Okay, what else can we do? I enjoyed loop rule so much, let's apply that again. So I'm going to start on the far side of the battery. I'm going to go across the battery. The battery gives us plus 9 volts. And you know what? I'm interested in finding out what's going on in this huge branch over here. So I go over here, and we have E. I do not know the potential across E, so I'm going to do delta VE. And then I keep going down. There aren't any other resistors. I end up back where I started. So according to loop rule, this must come up to 0. And we quickly find out that E actually has 9 volts across it, the entire potential that is, well, the same as the potential that is supplied by the battery, because it is basically in its own little branch. Now that does not mean that it has no effect on the circuit, but because it will affect how much current is coming out. Let's see, delta VE is 9 volts. Great. 9 volts. And now that I've got this filled in, I can apply Ohm's law. 9 equals our current times 10 ohms, 9 volts that is. So we've got 0.9 amp. Because I would have 9 divided by 10. Great. We're doing pretty well. There are some additional things that we can do now. Now that I know that I've got 0.3 amp going this way, and I will preface this by saying you may already be working on a different part of this. There's a bunch of different ways that you can actually go on this. I'm just seeing some of the things that I can fill in. I know that 0.3 amps goes down through this branch, and 0.9 goes through this. They're going to come back together and become the full 1.2 amp. And the total current going through our circuit, coming out of the battery and going back in the far side, is going to be 1.2 amp. As a result of that, I can also take 9 divided by 1.2 and find that the total equivalent resistance of our circuit should come up to 7.5 ohms. We're going to find out. Now, you may be thinking, hey, we could have gone in, we could have filled in D and then found the equivalent resistance, but I want you to stop and think about that. We found this very quickly and easily using Ohm's law. Doing equivalent resistance requires you to take it step by step. So while equivalent resistance can be a really good tool to use, sometimes it's not the best way to go about it. All right, let's go the alternate route, however, and take a look at resistor D. And for that, I'll grab orange. So let's apply loop rule, because we might be able to do something with the equivalent resistance, but that's going to be a whole lot of work, and I don't want to do more work than I have to. So I'm going to start on the far side of the battery. I go across the battery. That gives me plus 9. Now, the reason that I'm doing this is I need to fill one of these two in, so I'm either using equivalent resistance or I'm using loop rule. And like I said, I don't really want to do equivalent resistance unless I have to, so let's go with loop rule. I go across this. I go across resistor A, which we now know has a potential drop of 3 volts. I go in and we go this way. I go across resistor C, which we know has a drop of 2 volts. And then I go across resistor D, which we do not know, delta VD. Then we come back over here, and then we end up looping back around. We end up back where we started. So by Kirchhoff's loop rule, this must come up to 0. 9 minus 3, that's 6 minus 2, 4. So we end up with delta VD equals 4 volts. By loop rule, our potential difference across resistor D needs to be 4 volts. Okay, and let's go ahead and double check. So 4 volts equals 0.2 amps times our resistance. So 4 divided by 0.2 equals, this should be a 20 ohm resistor. Now we've filled in our table. There are a couple things that I want us to take a look at. First and foremost. All right, we had 0.3 amp coming this way, and 1/3 of it went this way, and 2/3 of it went this way, which means this has to be twice the resistance of this. Let's double check that. Now, the reason that I say that is, we talked about this in a previous video, and this can be very useful on the AP exam, that you're going to end up with the current splitting based on which path is going to be easier. Now, you may have seen in some of the other videos where I've talked about it, path of least resistance is misleading because it makes it sound like everything's going to go through just the simplest path, which is not true. It will actually split itself up. Since twice as much goes this way, it means that this must have half the resistance. Well, this side has a resistance of 60 ohms. This is 10 plus 20. This side has 30 ohms. It does match what we would expect. This is also something, as you're working through it, if you know that 1/3 goes this way and 2/3 go this way, when you get used to it, you could also come to the conclusion of, oh, this must have half of the resistance of the other side, and therefore the unknown quantity is 20 ohms. So those are some things that when you start getting used to this more and more, you might be able to cut some corners. Now, that can be kind of tricky, and it really only works if you've got really nice numbers that are working out. But neither here nor there. Let's see. Checking a couple of other things. So that's one thing that says that, hey, we probably got pretty good on our results. Okay, let's actually find the full equivalent resistance. I know that I wanted to avoid it, but that's what I would do if I were simply solving this, and I'd say that I'm done. But let's double check our results. We think the total equivalent resistance is 7.5. So I look here, and we've got, drawing this out like this, I'm going to combine these two, the 10 and 20, and they become pardon me, a 30 ohm resistor. That's their equivalent resistance. And we've got a 60 ohm resistor. Then I'm going to combine those as parallels. So that's 1 over 60 ohm plus 1 over 30 ohm, which is the same thing as 1 over 60 ohm plus 2 over 60 ohm, which is 3 over 60 ohm. Our equivalent resistance for that is going to come up to 20 ohm. Now, real quick, 20 ohms is less than 30 ohms and is less than 60 ohms. Once again, the total equivalent resistance for parallel must be less than any of the ones in an individual branch, or the collective for the branch, I should say. 20 is bigger than 10, but the total resistance of this is 30. All right, so now we've got that one as a 20, and we've got the following. If I were to redraw this, we've got A and now a 20 ohm resistor in this branch, and they are in series, which means I can add them directly together, and all of this section, A, B, C, and D, they all turn into, so this was a 20 ohm and this was a 10. The equivalent resistance for that entire branch is equal to 30 ohms. Great. And then we've got everything in this is in parallel with E. Now you can go through, you can check the current that goes through A, some of it goes through B, some of it goes through C and D. So A is in series with these, B is in parallel with C and D, while C and D are in series with one another. And E, because any of the current that goes through it does not go through any of the others, E is in parallel with all the rest of the circuit. All right, so drawing that out, let's see, I'm going to go ahead and erase this. We have basically this entire branch of the circuit simplified down into one thing. Oops, I should probably do that in green because it's an equivalent resistance. And we said that it was 30 ohms. 30. And then we had the other branch over here in parallel, which is 10 ohms, which means 1 over our total equivalent resistance is equal to 1 over 30 ohms plus 1 over 10 ohms. 30 ohms is going to be a common denominator, so this could also be written as 1 over 30 plus 3 over 30, which is equal to 4 over 30 ohms. Our equivalent resistance would be equal to 30 ohms divided by 4. And just double checking, but 30 divided by 4 is in fact 7.5 ohms. Now, you could have done this once you started filling some of the others in, but as you saw, I got that quickly and easily as soon as I knew the total potential difference for my circuit and the total current through my circuit. All right, so this is a complex and thorough problem. One of the things that I could follow up on, I'll leave this to you, is we could fill in the relative powers and see which things are getting the most power.